Virasoro Algebra take 35. For those of you who've just joined us or are joining late, let's do a brief review. Hey, what's up, math friends? Welcome back to yet another video done on the inside. It's supposed to rain today, and what I'm realizing is there's such a backlog of videos that I have to get them out the old-fashioned way before going back out into the field. I tried filming this video out in the field, and it just didn't work out. So hopefully this will be a little bit more concise and a little bit more coherent. Today, we're going to be talking about the Virasoro Algebra. Specifically, we'll be deriving for you the expression for the most general central charge that you can append to the width algebra. In a later video, we'll talk about how you determine the central charge based on representations. Okay, great. So let's get started. We begin with the Laurent polynomials, that is to say, those polynomials with complex coefficients with powers taking values in the integers. Let's call that C. You can think of C as a vector space. Indeed, you can think of C as the span of all monomials, say t to the m, where m is, again, an integer. In this case, t to the m represents a basis for C. You can see pretty clearly that there's a natural grading on this space. That is to say that we can consider each one-dimensional subspace spanned by each monomial, t to the m, as a space of homogeneous degree. And what is that degree? That degree, of course, is m. So we can formally write a degree operator for C as t d by dt, where now t is this formal variable, this Laurent polynomial variable, so that this operator d acting on any monomial t to the m gives us m t to the m. Very nice, very simple. Evidently, d is an endomorphism, then, of C. More than that, even, it's a derivation of C, as is clear because it's a derivative. The Laurent polynomials, this vector space C, shares a property that relates vectors to operators that we saw and have been contending with respect to the Heisenberg modules, those canonical Heisenberg modules. So given any polynomial p of t in C, we can think of that as either a vector in C, or we can think of it as an operator acting on the identity 1, right, just the number 1, that maps 1 to that polynomial p of t. Moreover, we can act on any other polynomial in the Laurent polynomials by p of t to get yet another polynomial. That is to say, it's an operator that will act on any vector, much in the same way that we talked about Heisenberg operators from the symmetric tensor algebra over H minus. The commutative property of polynomial multiplication is, is basically the same structure that the symmetric tensor algebra had, and that's why we have this kind of confusion between operators and vectors. But of course, just as M, the Heisenberg module, was not the complete set of endomorphisms of M, it is also true that C is not, of course, the complete set of endomorphisms of C. Well, in particular, we also have the degree derivation. We can get another derivation of C by simply multiplying the degree derivation by any polynomial p of t that we like. And indeed, we can construct an entire basis for the algebra of derivations by simply taking that basis from C. So that is to say, let's construct a basis for the derivations on C by doing exactly the same thing. We take, let's define an operator dm, which is equal to t to the minus m times d. We can construct an algebra of derivations by taking the span over all of these dm's, right, where m is now an integer. Or in particular, 0 is given by just d. Now, unlike the algebra of polynomials C, the algebra of derivations is not abelian, right? Because we have a derivative now. So let's define the Lie bracket to be the commutator of two elements and see what the algebra is. So the commutator of dm with dn can be worked out explicitly. I guess I should leave that for you as an exercise. And we're left with, of course, the quantity m minus n dm plus n. Right, this is the famous Witt algebra that Ernst Witt studied in the context of like finite fields or whatever. And that's a whole other story that's interesting in a whole different capacity, but we won't talk about that now. Strictly, we're going to talk about this algebra here. So the Witt algebra has another manifestation that we can think about. We can think about it as not just arising from the Laurent polynomials, but we can think about it as emerging from vector fields or holomorphic functions on the unit circle. To see that, let's parameterize the unit circle by some coordinate theta, right? And then we can expand any function of theta, right, in terms of a Fourier series. So sine theta, cosine theta. But, it's much easier for us, especially as physicists, to work in a complexified sense. So instead, we'll take a basis to be e to the in theta, e to the minus in theta. That is to say, e to the in theta for n some integer. And this can be used to represent, any smooth function from the circle into the complex numbers. So now let's make the identification, the obvious identification in retrospect, t with e to the minus I theta, right? So now we immediately see that c from this perspective can be thought of as a basis for functions, that is to say holomorphic functions, that is to say, vector fields, one-dimensional vector fields on the sphere itself. And from this, if that's a little too vague for you, let's think about it in terms of one forms, right? So a circle is a one-dimensional smooth manifold, compact, very nice. It has a one form on it, right? D theta. What is d theta? Well, let's look back at the degree derivation d from the perspective of the Laurent polynomials. That's just t d by dt. So taking this identification with t e to the minus I theta, we can simply realize that d itself, that derivation, is nothing more than just the one form, d theta. Cool. Awesome. So really what we found is that the derivations from the Laurent polynomials now just represent one forms on the circle. That is to say, it presents us with an algebra, an infinite dimensional algebra, that is the WIT algebra for this circle. And, if we just keep the definition dm as given by e to the minus im theta, d theta, right, we quickly see that we have an algebra with exactly the same commutation relations. Now the Lie bracket is the Lie derivative and blah, 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 blah. It still has the same structure, that is to say dm with dn is equal to m minus n plus, times dm plus n. Awesome. So that's very nice. So if you're wondering why the Virasoro algebra shows up all the time, well, what are two things that show up all the time in physics, especially in mathematical physics? One, holomorphic functions, that is to say polynomials, and two, circles. Circles show up all the time, especially in string theory, right? So go figure. So the main business of today is to extend this WIT algebra with a central extension. And there are a lot of reasons for doing so, mostly because it's forced, imposed, whatever, upon us from stringy physics. Let's just do the most general possible thing. So to study this extended WIT algebra, the so-called Virasoro algebra, let's just write down the most general thing we can. So we'll extend the Lie bracket. So dm with dn is given by m minus n dm plus n plus a central term, a new term, a term that's orthogonal to the rest of the vectors in the derivations. That is to say c. C is in the center, if you like, and then multiplied by some scalar function, f of m and n, which depend on the indices of the two basis elements from the derivations that we were putting in the Lie bracket. Okay, so our task is to determine what are the most general values of f, m, n that we can find. So the Lie bracket itself, by definition, will constrain these values of f and m on its own. For example, the Lie bracket is necessarily antisymmetric and satisfies the Jacobi identities. So it's antisymmetric or alternating, however you want to frame it. That is to say, given some element g in the Lie algebra, g with g necessarily always vanishes. So this implies that, for example, from the perspective of commutators, f with g is equal to minus g with f. So dm with dn plus dn with dm must be equal to 0. Okay, so the first term in the WIT algebra, that cancels out. That's no big deal. That makes sense. So the central term basically implies that c times f of mn plus c times f of nm must also equal 0, which can only be satisfied if f of mn is antisymmetric in its own right. That is to say, f of mn is equal to minus f of nm. Cool. Well, that tells us one thing right off the bat, right? That f of 0, 0 is 0. Indeed, f of mm with anything necessarily must be 0. Okay, now let's employ the second constraint on the Lie bracket, that is to say the Jacobi identity, which is, three three items bracketed together in all possible ways. That is to say, we have dm with dn, whole thing with d, say, k, right? And then you just take the other two cyclic permutations of m, n, and k and set that equal to 0. So this, if you carry it through, and you can do that as an exercise, gives you a constraint for f of mn, and I'll just write it out here. It's, m minus n quantity times blah, 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 all this stuff. So for us, there will be two special cases of these three arguments, m, n, and k, that will be important and enlightening for constraining the structure of f. So the first case we'll consider, we'll let k equal 0 and consider the case where m plus n is not equal to 0. Right, so this gives us an expression which relates f of m plus n 0 with f of m n and f of n m. So we can just, using the antisymmetric property that we've already discovered, we can collect like terms and simplify and realize that, okay, good, now we have concretely the relationship that f of mn is equal to m minus n divided by m plus m times this other thing, f of m plus n comma 0. Okay, so in other words, we can relate the two. Cool. Now, an argument that FLM uses, that a lot of folks will use and will use again in another context, is that we can shift the basis functions, these basis functions dm, by a constant term. So a constant term is obviously not going to affect the Lie bracket. We can add to dn a term 1 over n times c times f of n comma 0, just whatever that constant is. We can just add that term, and that will have the net effect of shifting the definition of the Lie bracket. So the commutator itself doesn't get affected because constants commute with everything, but that first term on the right-hand side, that Witt algebra term, has to be shifted to correspond to this new basis that we've defined. And yet, because, again, we're adding by constants, so obviously it's a Lie algebra isomorphism, not a big deal. But when we do that shift, what we find is that that specific shift we can use to cancel out any term of the form f of m plus n comma 0. That is to say, we can always find a basis functions for these dm dn such that the central term f of mn can always be written in the form f of m comma minus m. In other words, it's got this antisymmetric diagonal component to it, right? So in other words, f of mn is equal to f of m, whatever that is, times the Kronecker delta d, Kronecker delta m plus n comma 0. Good. So in other words, any central extension to the Witt algebra can be presented in this form. Cool. So now let's impose that constraint back on the original Lie bracket constraint from the Jacobi identity, and we find a relationship. And that relationship now relates f of m plus n, this new f, right, this diagonal version of f of m plus n with f of m and f of n. I'm going to leave this as an exercise, and I strongly encourage you to at least figure this one out, at least do this one out explicitly, because it's really instructive to making sure that you understand precisely how the computation works. So if you can get to here, you've pretty much got 80% of this video. Cool. Okay, so what do we have here? We have a recurrence relation, in effect, for f of m plus n. In some sense, it's a two-dimensional recurrence relationship, right? Because if I know what I know that f of 0, for example, is 0. We've already determined that by antisymmetry. But I know f of 1, which in our old language was f of 1 minus 1, right? And if I know f of 1, I know f of 2, I can compute f of 3 by just plugging in. Similarly, if I know f of 1, f of 2, and f of 3, I can compute f of 4, f of 5, and so on and so forth. I can compute them all. So I only need to know two solutions, in other words, to compute this whole thing out. So rather than doing that and trying to guess what values of f of 1 and f of 2 are, let's look for complete solutions to this whole thing. We know that f of m needs to be antisymmetric in the sense that f of m minus m, right, is equal to minus f of minus m, m, or f of m is equal to minus f of minus m, right? So let's just do the stupidest thing that we can think of and guess, is f of m equal to m a solution? So we plug it in, and sure enough, it's a solution. Awesome! So that's one particular solution. We only need to find one more. So in the grand scheme of things, what's the next obvious thing that you can guess? Well, what's the next odd monomial in m, right? M cubed. So let's try that. Once again, you can work through the computations yourself and find, sure enough, m cubed is also a solution. So that's it. We're done. We've got two solutions to this recurrence relation. And so what we find is, therefore, that the most general central extension that we can write down is a linear combination of two terms. Let's call it alpha times m plus beta times m cubed. right? So in other words, the entire Lie bracket can be written for dm with dn is equal to m minus n dm plus n plus c times the quantity alpha m plus beta m cubed times that Kronecker delta that enforces the diagonal condition delta m plus n is equal 0. Awesome. So that, in a nutshell, is the Virasoro algebra. But there is more to say. So remember that change of basis trick that we did earlier? You can do this again, and this is worth pointing out, and it will be crucially important for things that we discuss when we start talking about the monster CFT, and generically when we start employing these tactics for the study of vertex operator algebras. So let's do another shift of these DMs, these now shifted DMs that got rid of those diagonal terms. Let's do another shift, and let's shift by how much? Let's shift by some constant alpha c delta m comma 0. Cool. And so when we perform this additional shift, this extended shift, this new shift, what do we find? Well, let's plug it back through the Lie bracket just like we've seen before, and what we've found is we can actually use that term to cancel out the alpha term. Put differently, while it is true that the most general form of the Lie bracket has two parameters, alpha and beta, we can always shift our basis in such a way that we can eliminate alpha. Alpha doesn't really matter in some respect, whereas the value of beta does. We'll never be able to get rid of the beta m cubed term in this fashion. Now, you can rescale beta by simply rescaling the definition of the central charge, as we'll see. So suffice it to say, there's a convention. That convention fixes the normalization constant of C, and that convention fixes the particular value of A that we are using. And that convention is what we normally write down when we write down the Virasoro algebra. So in other words, we can write down the Lie bracket of dm with dn is equal to m minus n dm plus n plus c over 12 times quantity m minus 1 times m times quantity m plus 1 times that Kronecker delta again, delta m plus n and 0. And that's just a convention. The most general thing, again, involves the alpha and the beta, but we can move things around as needed. There is one comment. Well, okay, so first, you probably want to convince yourself that that shift and the shift that we did originally do not interfere with each other, right? But that's what it means to shift by a constant. But oops, I gave it away. Convince yourself of that. But the final thing I want to point out is from this convention derives all of the values of the central charge. In other words, if we agree that we always write the Virasoro algebra in this way, the question is, okay, what now is the value of the central charge? And that, my friends, is going to be representation dependent. The representation of the Virasoro algebra that you are employing is the thing that will specify the central charge. Now, we will discuss this specifically next time, but just as by way of a hint, for the case of the Laurent polynomials, the central charge is fixed at 0. For the case of, the free scalar boson in conformal field theory, you already know what this is, right? The central charge is fixed at 1. For the case of n scalar bosons in a conformal field theory, the associated Virasoro algebra has a central charge fixed with n. And what we've already seen when we studied the twisted vertex operators previously is that when we construct our Heisenberg algebra, right, and use that Heisenberg algebra, which we'll do next time, to build out a representation of the Virasoro algebra, the dimension of the underlying vector space that we pushed forward using that Heisenberg functor, that dimension is the value of the central charge, at least under these current, under this particular convention. Cool, awesome. Anyway, great. Sorry we were not out on the trail today. I hope that wasn't too much of a bummer. It's raining anyway, and I promise I will send as much outdoor information, video, etc. at you as I possibly can in the coming months. But I just want to get this out there so that we can move on and talk about the interesting stuff. I keep saying that, but there's so much to do. There's so much to say. Specifically, determining the value of the central charge from the representation of the Virasoro algebra. Anyway, whatever. That's all for today. I hope you folks are having a fantastic spring. For you Northern Hemisphere folks, a fantastic fall for you Southern Hemisphere folks. I will talk to you as soon as I can. Be well.